Hello Gems, welcome back to a brand new series. In this series, we intend to target your 11th and 12th standard chapters in one shot. So you don't have to spend hours and hours of your life behind a single chapter. So those who intend to follow this series may consider subscribing. Today we are starting with the chapter Electric Charges and Fields, which is your 12th standard chapter 1. Okay, so this series is perfect for all levels and it's relevant for all competitive exams like BITSAT, JEE and NEET. So with that being said, let's cut the crap and begin. I've divided this chapter into 15 major sections and we'll be dealing with them one by one. So the first section is about the basics of charge. So what is charge? Charge is the intrinsic or inherent property of matter. Okay, it's present by the very nature of matter. So what does matter comprise of? It comprises of atoms, right? And what is atom made up of? Electrons, protons, neutrons. So due to the very nature of the atom, we have the charged particles. So charge is the intrinsic property of matter. Okay, and generally atom is neutral. And what do we mean by neutral? That there are equal number of positive and negative charges. Okay, the SI unit of our charge is coulombs. That is how you spell it, and it is denoted by capital C. Now 1 coulomb is a very big unit, as you'll come to see in the following section. So we, for practical purposes, we usually use microcoulombs, which are smaller units. Okay, 10 to the power minus 6 coulombs. Okay, so but the SI unit is coulombs, capital C. Okay, so there are two types of charges, as you know, positive and negative charges. Okay, so if you have a body, suppose what causes positive charge is the deficiency of electrons. Okay, so if you have a body, suppose this one, and it is neutral. Okay, now you rub it. Now you can induce charge by different methods. We'll discover them in the upcoming section. So if we rub it, suppose with some special cloth, okay, such that this body, some electrons from this body are scraped to that body. Okay, some electrons are removed. So this causes deficiency of electrons in this body, which means this will get positively charged. And the other way around, you can see that the some electrons move from this body to that, right? So there is excess of electrons on that body. So that body will become negatively charged. Okay, so those are two types of charges caused. So the positive charge is due to deficiency of electrons, the negative charge is due to excess of electrons. Okay, so let us try and handle this question now, which is based on the concept we learned just now. Okay, so let's read it. M is the mass of a neutral body. Okay, the mass of the same body when charged positively and negatively is m1 and m2 respectively. So m1 is the positively charged mass, m2 is the negatively charged mass of the same body. Okay, so you have to find a relationship between them. Now logic says that charge and mass are two independent quantities, right? They should not be related, and this should be the correct relation. It's actually not. Okay, just now I told you that positive charge is deficiency of electrons and negative is the excess of electrons, right? So basically there is transfer of charge from one body to another, right? So in case of the positively charged, there is deficiency of electrons. Some electrons are removed from that body, which means that its mass will decrease, right? Because electron itself has some mass. It's very less, but it has some mass, right? So the positively charged will have some deficiency of electron, less of electrons, so its mass will be less. Whereas the negatively charged will have excess of electron, its mass will be more. So neutral will come in between them. So positively charged, least mass because of deficiency of electrons, m equal number of neutrons and electrons and protons, and capital M2 that will have excess of electrons. More electrons, more mass. So option B is correct. I hope you get the idea. Let's move to the next section. Section 2 will be discussing about conductors and insulators. Now yes, of course we have started with the basics and this might seem very trivial, but as we proceed the sections are going to become challenging. Okay, so hold on for the challenges. Okay, so let's go briefly through them. So conductors, as you might know, are those materials that allow charge to flow freely through them, charge or flow of electric current through them. Okay, so the examples will be anything like metals. Okay, so you have gold, copper, aluminium. Graphite is a non-metal, but it also conducts. Okay, then why do metals conduct? Because there is this, you might know this concept of sea of electrons, that the valence electrons of the metal are loosely bound. Okay, they can move over the entire surface. So they contribute to conductivity of the metal, and electrolytes conduct basically due to ions. So if you have sodium chloride and you dissolve it in water, so it will break up into its component ions, which is Na plus and Cl minus, and these ions lead to conduction. right? So that is how electrons and metals and electrolytes conduct. Okay, this is due to electrons, this is due to ions. Okay, let's come to insulators. Insulators will be also referred to as dielectrics as we proceed with the next chapter onwards. Okay, so these are materials which do not allow electric current to flow through them. Okay, so basically you can have n number of examples like dryer, porcelain, wax. Porcelain is a piece that you use for uniform water bath. Okay, so you might have used it in chemistry, I don't know, I'm not sure, but you can add your own examples. So basically those materials that do not allow electricity or electric current or charge to flow through them. Now semiconductors are special type of materials. Okay, there is a whole chapter based on them. Okay, so the examples basically are silicon and germanium. Okay, those are intrinsic type. You will learn more about them in the chapter 14. Okay, they are very fascinating. Okay, they have conductivities between conductors and insulators, but there are properties which render them very useful. Okay, more useful than the conductors. Okay, so we'll learn about them in a special chapter. So for now you can just remember the example and let's move to the next section. Discuss about the different methods of charging. We have three of them. First one is charging by friction. Okay, so you can produce a charge by rubbing two bodies against each other. So an equal and opposite charge will be produced on them. So let us suppose this happens only with special kind of material. So let us suppose we have this pen and we have this cloth. Okay, so if we rub one against the another, okay, so what will happen? Some electrons from this will flow over here. Okay, so this has excess of electrons, so this will be negatively charged. This has deficiency of electrons, some have moved from here to here. So deficiency of electron, this is positively charged. This is what I familiarized you with in the first section. Okay, so this happens only with special kind of material. I don't know if it happened in this case, but some special materials with which this you can see this happening is glass rod and silk. So if you rub a silk cloth with a glass rod or glass rod with a silk cloth, negative charge will come on the silk cloth and positive will come on the glass rod. Okay, so some electrons have been transferred from the rod to the silk cloth. Okay, now if you rub fur, cat fur with ebonite rod, this is also a special kind of material. Okay, so this will get negatively charged. So fur has electrons basically, so this will move from the fur to the ebonite. So ebonite will become negatively charged due to excess of electrons and fur will become positively charged. Okay, so you can remember it that way, this way, that this is E for electron, E mane negative. Okay, so that is how you can remember that ebonite will be usually negatively charged, ebonite rod will be negatively charged, glass rod will be positively charged. Okay, so now you can also see this example when you were young, you might have been a scientist yourself. Okay, so dry hair and comb, if you run comb through your dry hair, and you can actually see it attract bits of paper, right? So why does that happen? Because dry hair has some electrons, excess of electrons, so that can be captured on your comb. Okay, so it becomes negatively charged and that can help attract the bits of paper by polarization. That is a different mechanism, but yeah, you get the point. The two pair of material can be equal and oppositely charged by rubbing them against one another. This is charging by friction in a sense. Okay, so this happens because transfer of electrons from one body to another, which renders one lack of electrons and other excess of electrons. So positively charged and negatively charged. Okay, so let's come to charge by conduction. This is very obvious. You just one of the body is charged and you bring it in contact with some other body, which is a conductor. Okay, so in that case charge will flow and you'll have so when you separate them, there will be some charge on both of them. Okay, so two bodies brought in contact, at least one of them is charged, develops a charge on other. Okay, provided we have both the conductors. Okay, so there might be equal splitting of charge or unequal splitting of charge. This depends on potential, right? Current only flows when there is difference in potential. So if you have two identical bodies, suppose two identical spheres, on one sphere we have plus q charge, okay, other is uncharged, so when you touch them there will be equal splitting because they are identical bodies, right? So basically the potential here will become equal when the charges are equal in this case. Okay, in case of sphere. Okay, so in case of symmetry you will have equal splitting of charges, and in case of two different types of materials, so these are not identical. Okay, so suppose this is ebonite rod negative Okay, so and here we have a sphere. Okay, so when you touch them, there will be flow of charges, but it might not be symmetric. Okay, so it might not be equal splitting of charge. Okay, somebody might get more, somebody might get less. Okay, depending on the potential. When they are kept touch, the charges will flow up till the potential is equal. Okay, so that depends on potential. If it's identical, there is equal splitting. If it's not identical, you can't say. Okay, there will be unequal splitting. Okay, let's come to induction. This is the one which we are going to use most. Okay, so induction is merely charging without contact. Okay, you can induce some charges by bringing, like suppose we have, I'll give you an example. We have a metallic sphere. It is placed on an insulating stand. Okay, so basically it does not allow the flow of charges to the ground. Okay, so we have this setup over here, and we have this glass rod, positive, right? So glass rod, we bring it close to this metallic sphere. We don't bring it in contact, we bring it close. Okay, so it's close. So this positive charge will attract the electrons in this metallic sphere, right? Electron, sea of electrons, you remember, right? So it will attract the electrons towards this side, right? Towards the positive side, right? Unlike charges attract. Okay, so negative charge will be attracted over here. Okay, and similarly positive charge will be developed on the other side due to deficiency of electrons. Okay, so negative charge comes over here, and positive charges developed on the other side due to deficiency. Okay, so as soon as you remove this rod, so now if I remove this rod, the charges will fizzle out. Okay, they will again come to their original distribution, and they will cancel out each other. So the charge will disappear. So as soon as you remove the rod, the charge on the sphere will disappear. Okay, so we can use this actually to positively or negatively charge a sphere. We'll see that in one of those questions. Okay, so these are the, in brief, the three ways of inducing charge on a material. Okay, by friction, by conduction, and by induction. Okay, you can note it down, and let's move to the next section. Section 4, here we'll discuss the properties of charge. So first one being the very obvious one, that like charges will repel and the unlike charges will attract. So for instance, if we have positive and negative, two different type of charges, they will attract each other, they will draw each other closer. Okay, and if we have like charges like plus q, minus q, minus q, they will repel each other. Okay, these two will repel each other, these two will repel each other. Okay, and these two will attract each other, unlike charges. Okay, let's come to the second property, which is conservation of charge. Okay, this was always in the shadow all the while that we discussed this, because as I was mentioning, every method of charging, there was transfer of electrons from one body to another. Okay, in any case you would not have seen charge being created or destroyed. Okay, and that is very fundamental, that charge can neither be created nor destroyed, it can only be transferred from one body to another. Okay, just like the principle of conservation of energy. Okay, it is conservation of charge. It also means that if you have a charge, okay, charge on an isolated system, okay, if you have a sphere, you have put some charge on it and you leave it straight, okay, you don't disturb it, you don't bring no charges close to it, okay, it's left in vacuum, isolated system, okay, that charge will remain constant, it will not change. Okay, so you might have seen in the case of induction too, when you brought a rod closer, positive rod, right, negative charge was induced. Okay, it was not created, it was induced, and similarly positive charge was induced. Okay, so those, if you see, once you remove the rod, those charges cancel out each other. Okay, so they were induced charges, they were not created or destroyed, they were induced, and they were induced in equal and opposite sense. Okay, so charge by very nature in a body cannot be created out of somewhere or destroyed. If it's there in the body, it cannot be destroyed. Okay, since it's the intrinsic property of matter, right, it all connects. Okay, so that is the second property. Coming to the third property is quantization. Now this is a bit challenging. Okay, so let's learn it. So it says that charge is quantized. Okay, so basically any charge that you have can be expressed as integral multiple of E. E is some fundamental value, it's the charge on electron if you ask me. So it is 1.6 into 10 to the power minus 19 coulombs. Okay, so that is the value of E, and N should be some integer. So any charge that you have in this world should be expressed in the form of N times E. Okay, where N is a integer. Okay, so charge is quantized, it can be expressed as integer times some constant value. Okay, now this fact is microscopically ignored. Okay, so basically we'll see it in an upcoming question, that if you rigidly stick to this fact, 1 coulomb itself cannot exist. Okay, But for large charges, 1 coulomb is a very large charge. You will come to know when we discuss that problem. So for large charges, you can see that this Q will be very large, right? For large charge, Q is large. So E is constant, it is very small, you can see. So this N will be very large, okay? So we do not stick to integer, okay? For practical purposes, naturally, N should be an integer, okay? Everywhere, every charge you see in nature is of this form, okay? But macroscopically, we ignore that fact, okay? Since N is so large that we can ignore this fact, okay? So macroscopically, where we have in practical cases where we'll have large charges, we'll ignore this fact, okay? So although it is true in nature, okay? So charges like E by 3, 2E by 3, so some fractional value of E, these charges do not exist, okay? Although we have found quarks, up quarks and down quarks which have charges like this, but those don't come in our discussion, okay? Those are not very fundamental charges if I speak of. These charges actually should not exist, okay? So that's the long story short about quantization. And finally, charge is a scalar, but it can be positive or negative. Being positive or negative does not make it a vector, okay? It does not show any direction. So it's just a property. It can be positive or negative, right? Those are two types of charges. It's scalar, but it's a scalar quantity. It has only magnitude, okay? So those are the few properties of charge. Let's go to two more problems which will enhance our understanding on this topic. Let's come to these two numericals now. Here, before that, let me come to this point which I forgot to mention last. When we discussed property 1, we said that like charges will repel and unlike charges will attract. Okay. However, there is a very rare case that is actually generally true for your point charges. Okay, it's actually universally true. We'll see what happens over here. Okay, so in case suppose we have a large positive charge and a small positive charge. Okay, this is a very large positive charge and this is a small positive charge. In this case, we see that these two will attract each other. Okay, rather the large one will attract the small one. Okay, why does this happen? Okay, so they are like charges, right? Why they are attracting each other? Actually, it happens due to induction. Okay, this large positive charge, mind you, these are not point charges. Okay, these are very big charges. Okay, so this large positive charge is creating negative and positive charge by induction on this negative charge. Okay, so it's splitting about, it's tearing apart the negative charge and the positive charge. Okay, so the negative charge is attracted towards the positive charge, and that is the reason of attraction of this small positive charge to this large positive charge. Okay, so in a sense, if you see, the law is not broken. Still you can see that this is a positive charge. It has created negative charge on the smaller positive charge. That's why the unlike charges are attracting each other. Okay, so that is a very rare case. You must keep that in mind. Okay, so let's come to this numerical. How many electrons are there in one coulomb? Okay, so we can use the relation Q is equal to Ne. We know that charge is quantized. Okay, any charge can be expressed as N times E. Okay, so 1 coulomb will be given as N times E. E is 1.6 into 10 to the power minus 19. Okay, so if you solve this, 1 by 1.6 is 0.625. Okay, and this will be 10 to the power 19, right? Or you can write this as 6.25 into 10 to the power 18. Okay, you can see that how huge is this number, right? This many electrons, 6.25 into 10 to the power 18. Okay, this many electrons for 1 coulomb. So that's why I said 1 coulomb is a very large charge, right? We do not use it practically. Practically, we come across the order of 1 microcoulomb, 10 to the power minus 6. So that is what we'll usually use, because 1 coulomb is itself a very big charge. Okay, and one more, if I mistake I made in the last section, which I said that 1 coulomb should not exist by nature. Okay, it will exist because N is an integer. You can clearly see it. You just have to shift the decimal. There are 18 zeros after that. Okay, so that was a mistake on my part, sorry. 1 coulomb will exist. So basically for large numbers you can ignore this quantization, because these numbers are so large that it's insignificant for to count individually one electron. Okay, so yeah, so basically 1 coulomb is this many electrons. It's a huge charge. Okay, let's come to this one. Charge a sphere positively by induction. Okay, how can we do this? So if we want to charge positively, we have to separate out the positive charge, right? So how can we do that? We can bring negative rod. Okay, so we'll have the same apparatus of that of induction. Okay, so this is the insulating stand, metallic sphere. We'll bring the will bring a positive charge, or will bring a negative charge close to it. This is ebonite rod, you can say, okay, since it is negatively charged. Um, then we can say that this will produce charges of plus over here by induction, right? This negative sign will repel these electrons in this side of the region, they will move to the other side. So plus side, positive charge will be produced on this side of the sphere, okay. Now what to do next? We'll keep the rod as it is, because if we remove the rod, the charges will disappear, you know that, right? So we'll keep the rod as it is and we'll ground the sphere, okay. We'll connect this side of the sphere to ground, so that the negative charges, the electrons, basically flow through to the ground, okay. So anybody can tell me if ground is a good conductor or not, okay. Do let me know the answers in the comment section. Is the ground, is the earth a good conductor or not, okay. So these electrons will flow over here into the ground, and basically you'll have only the positive charge, okay, which is kept intact due to this rod. We have hold this rod, okay. So now you can remove the rod, okay. Once you remove the rod, this charges will redistribute, okay? They will redistribute over the entire surface and you'll get a positively charged sphere, okay. So it's very simple. So you want to create a positively charged sphere, you bring a negatively charged rod, so that you can isolate the positively charged positive charge, right? So you bring the positives over here due to the negative rod, negative on the other side, you can ground it so that the electrons flow to the ground, okay. You have only the positive charges left, which are still kept intact due to this rod. Once you remove that rod, they will distribute over the sphere and you will get a positively charged sphere. So similarly, you can charge negatively, and that is the way to do it. You just have to change the type of rod. You will take a positive rod if you want to charge negatively, okay. So that's about this section. Over to the next section, to the most important part of the chapter, which is Coulomb's law. Now Coulomb's law was formulated based on experiments on point charges, so it is valid for point charges, may not be valid for extended charges, okay. So the statement goes this way: the electrostatic force between two point charges, now point charge is the key word over here because it is valid only for point charge, okay. So the electrostatic force between any two point charges, here let us take Q1 and Q2, is directly proportional to the product of their charges. So force is directly proportional to the product of charges Q1 times Q2, and inversely proportional to the square of distance of separation between them. So inversely proportional to the square of r square, the distance of separation, okay. Here we have considered unlike charges, so they are attracting each other. Now one more important point to remember is that the force will be along the line joining the two, okay. So Q1 and Q2, you can join them by a line, okay, and you can see that the forces of attraction, in this case this we have considered unlike charges, so they are attracting each other. So you can see that the force is along this line which is joining the charge Q1 and Q2, okay. So even if in case if we had both positive charges, I mean like charges, then they will repel each other, right? So in that case too, the forces will be along the line joining the two charges, okay. You can see this is the line joining the two charges. The force is along the line joining the two charges Q1, Q2, okay. That is a very important point to remember, okay. Now force is a vector, but for our purposes now we'll just consider the scalar part, so we'll take magnitude, okay. Later we'll see the vector form of Coulomb's law. So for now let's only consider the magnitude. So this proportionality can be converted into our equality by multiplying by a constant. This constant is k over here, found through experiments. K is defined as 1 upon 4 pi epsilon naught, okay. This has a value of 9 into, this is something that you would want to remember. So it has a value of 1 upon 4 pi epsilon naught, okay, and the value is 9 into 10 to the power 9, okay. The units are Newton meter square by Coulomb square. You can easily see that. So it's Newton meter square by Coulomb square, units of K, right? Newton meter square by Coulomb square, okay. So this epsilon naught over here is another constant. It is called permittivity of free space. It is very useful in the discussions of electromagnetic waves. We'll come to that in very later chapters, okay. So epsilon naught, for now you remember it is permittivity of free space, okay. It has a value of 8.85 into 10 to the power minus 12, and since it is inversely related to your K, the units will be just inverse, okay. Coulomb square by Newton meter square, okay. So if you plug in this value over here, you'll get 9 into 10 to the power 9, Okay, so epsilon naught itself has a value of 8.85 into 10 to the power minus 2. Now this is for free space. Free space meaning vacuum. Okay, so in other cases, suppose you have placed two charges in some other medium other than vacuum. Okay, so that medium will have its own different properties, its own permittivity. Okay, this is for vacuum. Okay, the other medium will have its own other permittivity. Okay, that can be obtained. So the permittivity of the other medium can be obtained by multiplying the constant by epsilon naught. Some constant, it will be usually mentioned in the question. This is called relative permeability. Okay, a permittivity. Sorry. So this is epsilon r is relative permittivity. Okay, it will be given when the medium is changed. If the medium is some other medium other than vacuum. Okay, so you just have to transform this epsilon naught to epsilon. Okay, useful in problem solving. So keep it in mind that if you have placed two charges in some other medium other than vacuum or air, this epsilon naught will transform into epsilon, where epsilon is given by epsilon r times epsilon naught, and epsilon r is relative permittivity. Okay, so far so good. And also one more point, that you can see the nature of these forces by the sign. Okay, so if we ignore the magnitude, okay, we don't take the magnitude, okay, you can see that force will be given as k q1 q2 by r square. Okay, we are ignoring the magnitude. Okay, so now if we have two unlike charges, what will happen? Unlike charges will give a negative sign, right? Negative sign meaning the force is of attraction. Okay, so it can all be connected. Okay, so if you have like charges, it will give positive charge. So if you see in the case of gravity, gravity is minus gmm by r square, right? Minus because gravity is always attractive, right? So in this case, if you have the forces of attraction, the two charges should be opposite, right? They should be unlike in order to attract each other. Okay, so two different charges will give a negative sign, which means attraction, and two positive charge or two negative charge, which are like charges, which will repel each other. They will give negative times negative is positive, so the force is positive, it is repulsion. So you can also remember it this way, or you can think about this way, like an unlike charges. Okay, so let's come to the properties of uh, Coulomb, Coulomb force, or this law, Coulomb's law. There are three properties. We'll just see the first one now. We'll see the other ones in the subsequent section. Okay. So the first property is the superposition theorem. So basically, if you have two charges which are exerting a force on the third one, you can find the total force which is acting on the third one by the vector sum of the two charges, the forces that the two charges exert individually. Okay, so suppose if you have two charges 1 and 2 which are exerting force on third one, so 2 is attracting, you can see 2 is attracting, and the force is along the direction joining the two. Yes, it's true. And 1 is pushing it away, you can see that. Okay, so the force is again along the line joining the two charges. Okay, so these two are the forces, I can say F2 and F1. So this F net will be given as F1 plus F2. Okay, the vector sum. I hope you know how to add the vectors. You can see, you can use the parallelogram law over here, or you can use the magnitude of the vector under root F1 square plus F2 square plus 2F1 F2 cos of theta, right? So that is the way how you add two vectors, and in case the two vectors, in this case the two vectors are the forces over here. Okay, and again this definition can be extended to n different particles. So you can have n different particles exerting force on your particle of choice. So this is your, suppose the third particle, you can have 1, 2, I'll call it some p particle. Okay, 3, 4, and then nth particle. So you can sum up all these forces. So in general, you can write the general superposition theorem, that the forces acting on a particle will be the net force acting on a particle due to all other charges will be the vector sum of all the forces which they exert individually. Okay, so you can write the general statement as well. Okay, so that's about superposition theorem. We'll learn two more properties in the next section, and we'll also solve a numerical which will enhance the idea of this concept. Okay, so over to the next section. So let us now discuss briefly the remaining two properties and a numerical, just an illustrative one to get you the hang of the idea. Okay, so let's come to property number 2. Here the two forces that the two charges exert on each other are equal and opposite. Okay, so this electrostatic forces are in accordance with your Newton's third law. Okay, so they are equal and opposite. Okay, we'll see, we'll prove it, we'll write the forces in vector form, and we'll prove that it is in accordance with your Newton's third law. Okay, so we'll choose an origin over here. So we have these two charges q1, q2, which are placed in space. Okay, r1 is the position vector to q1 from origin to q1. R2 is the position vector from origin to q2. Now this vector can be easily seen that it will be r2 minus r1, basically triangle law. This is r1, this is r2, and this is r2 minus r1. Or you can see that r1 plus r2 minus r1, r1 will get cancelled and you'll get r2. Okay, so basically by the triangle law you can find this as r2 minus r1. Okay, now we have considered two like charges, so they are repelling each other as you can see, and the direction is along the line joining the two, okay, away from each other. So the force in the first case, now we are writing it vectorially, keep that in mind. So the first part will remain the same. So force is your constant times the product of the charges divided by the inversely proportional to the square of distance of separation, r2 minus r1, the magnitude of that distance, right? So that's squared, right? Now we also have to specify the direction, right? So F12 is basically, what do we mean by F12? This terminology means that force on 1 due to 2. Okay, F12 means force on 1 due to 2. Okay, now if you see the force on q1 due to q2 is along this direction, right? It's along negative of r2 minus r1. r2 minus r1 is along that direction. It is along r1 minus r2, which is r12. So basically r21 means r2 minus r1, right? So r12 is r1 minus r2, which is opposite of that. Okay, so F12 is along r12, this direction. Okay, now similarly let us find out the force on the second one due to the first one. So F21, force on the second due to the first, force on second due to first. Okay, so similarly by Coulomb's law, k times product of the charges divided by the square of distance between them, fine. And here, so basically this cap denotes unit vector. Okay, so it will not affect the magnitude, it has a unit magnitude, but it only shows the direction. Okay, so here if you see, this force is along r21, right? r2 minus r1. So you can basically say that it is along r21. Okay, now you can see that this is r1 minus r2, so this part is same for both. Okay, this part is same, this is r1 minus r2 and this is r2 minus r1, so which means they are negatives of each other. Okay, although the magnitude is the same, this is just a unit vector, its magnitude is 1, it will not affect the magnitude. Okay, magnitude is same, direction is opposite. The forces that two charges exert on each other are equal and opposite. F12 is minus of F21. Okay, and some books they will write the vector form in more elaborate way. They will write r12 as r2 minus r1. Okay, r21 is r2 minus r1, and then they will use that the unit vector can be expressed by the magnitude divided by the vector divided by its magnitude. So you'll see a cube coming in the equation. Okay, so they'll use r1 in place of r21, they'll use this r2 minus r1 upon r2 magnitude of r2 minus r1. That is how a unit vector is defined. So you'll see a cube term over here, which is due to this and this will get multiplied, and you'll see a cube term. Okay, so that is not completely wrong, that is true. Okay, so that way you can also see it, but this is enough, I believe. Okay, so don't get confused if you see a cube term over there. Okay, so it can be written this way and you can get the cube term as well. You will see that in your NCERT. Okay, now finally the last property is that these electric forces are conservative. Now conservative forces is a topic in 11th standard. I hope you remember tidbits of it. Okay, so basically if you want me to tell you in short, that it is path independent. Okay, and that is one major property, and basically the force, this force can be expressed, the conservative force can be expressed as some negative gradient of potential energy. Okay, now for you gradient is a very heavy term. We'll just say negative derivative. Okay, it's very loose, but take my word for it. It won't cause you troubles, at least in this stage. Okay, so it's you can express the force as negative derivative of potential. Okay, so that is what is meant by conservative force. So the laws of conservation will be also held in this case. Okay. So now let's come to this one. This is a illustrative problem. We have Q1, Q2, Q3 at the vertex of equilateral triangle of side 1 meter. Okay, this each side is 1 meter of this equilateral triangle. You are supposed to find the net force on charge, this 1 microcoulomb charge. Okay, so it's very simple. Okay, I'll just go through it. So if you see, we can use the superposition theorem. The F net force on this charge will be due to this one and due to that one. Right? Due to this one, you can see it is along the line joining the two, and it is repelling. Right? Positive charges. Positive, negative. This force is attracting. So you have F1 and F2. Now you need not consider the sign in first case, because directly we are going to add these vectors at an angle of 120 degree. Right? This is an equilateral triangle. This angle is 60 degrees. This is a line, so the remaining angle is 120 degrees. So F1 and F2 are at an angle of 120 degrees. Okay, so you need not consider the sign. We will directly add the vectors. Okay, so basically consider this form, and finally we'll add the vectors. Okay, here the signs are not considered of the charges. Okay, so first one, F1, due to this charge, k q1 q2 by r square. R is 1, k is this, q1 is this, q2 is this. Okay, solve it, you'll get this. Now F2, if you see, will be due to this k q1. Q1 is this without the sign. So basically you take the magnitude, so sign goes that way, and q2 is this. Then solve, you'll get F2. So you get F1 and F2, and basically you'll have to add. So to find the magnitude of the net force, you can use this relation. This is the vector addition. Here theta, you can see that the angle between two forces is 120 degrees. So F1 square plus F2 square plus 2F1 F2 cos theta, and the answer that you'll get is 2.38 into 10 to the power minus 2 newtons. Okay, so you can try it yourself. So let's move to the next section. So let us now understand the concept of electric field. Now electric field was an imaginary concept that was developed to explain this interaction between the charges, just like gravitational field, right? So to explain gravity, we had gravitational field, and to explain this Coulomb's law and the forces, electrostatic force, we have the electric field. Okay, so basically it's mathematically defined as limit q tending to 0. So this q naught is the test charge. We'll see in while what it is. F divided by q naught. Okay, so basically we assume that there is a source q. Okay, this is a bigger charge. Okay, and this q naught is a very small charge tending to 0. We'll see why it should tend to 0. We'll call this test charge. Okay, and source is producing this electric field. Okay, it's producing electric field all around it. Okay, and that electric field is influencing this charge q naught. Okay, that is the reason of interaction between these two. Okay, that is the reason why one charge is exerting a force on the other. Okay, so this electric field, as I told you, is an imaginary concept to explain this interaction. Long story short. Okay, so the sources produce electric field, and due to which there is a force on the test charge. Now this q naught, we said it should be very small so that it does not distort or influences the field of your source. Okay, so we are testing the field due to discharge. This charge should not be significantly large so that it itself affects the field of this one. Okay, we'll see the field lines and you'll get the feel of it in the next section. Okay, so for now this is a small charge so that it does not affect or influence the field of this. We want to find the field due to this charge, so that to find the influence due to this charge, so that that charge should not be very large and influence the field of first one. So we take limit q naught tending to 0. Okay, so the test charge should be very small. Okay, now the force is along E. As you can see, force and electric field are related by this relation. So you can basically write F is equal to QE, right? So the force will be along the direction of electric field. Okay, positive or negative depends on this charge, right? So either it will be along the direction if it's a positive charge, and if it's a negative charge it will be opposite. F is equal to minus times E, right? So either it will be parallel to the direction of electric field or anti-parallel to the direction of the electric field. So this electric field concept is also explaining the direction of force, right? So we find that the point charge, the electric field due to a point charge is this relation. Okay, In this class we are not doing any derivations, we are not focusing on derivations. That will stretch out the one shot video. So we'll have the derivations in one more session. We'll call it one shot derivations. Okay, so if you want to follow that, you may follow that. Okay, so in that we'll be deriving all these relations that we are skipping over here. Okay, here we are just assuming that this is falling from heaven, but in those lectures we'll be deriving them. Okay, so that is the electric field due to a point charge. Okay, so point charge q, suppose it's k, here is a familiar term, it's kq by r square. You can remember that way too. Okay, so superposition theorem holds for electric field too. So if you want to find the electric field on third one due to two more charges, you can add them vectorially. Okay, so E net on the third one, or in general E net on a particular or charge will be due to, or at a particular point. Okay, the electric field at a particular point will be sum of the electric fields due to the other charges at that point. Okay, vector sum, very important. Now let us come to this numerical. This is a very favorite numerical for your competitive exams. It has shown multiple times. So here we have Q1 and Q2, 16 microohms and microcoulombs and 4 microcoulombs separated by 3 meter distance. Find a point where the net field between them is 0. Okay, so we'll assume that it is at a point x. Now I'm very careful as I'm drawing this x, because it will be more closer to your 4 microcoulombs than 16, right? Inversely proportional. So here the field due to this one and this one should cancel. Okay, or field is directly related to force, so field becomes 0. Force should also become 0 at that point. Okay, so I'm placing it more closer to 4 coulombs, the smaller charge, because I know why. Okay, basically it's inversely proportional to distance, right? So it should be at a larger distance from your bigger charge, so that these two forces are equal and they cancel out each other. Okay, suppose let us assume that at a distance x it is becoming 0 at a distance x from the 16 coulombs. So this distance will be 3 minus x, obviously, right? Total distance is 3, so this is 3 minus x, right? So this electric field at that point, so due to this first charge and second charge is equal, right? They are equal in magnitude, opposite in direction, so I am equating their magnitudes. We know that electric field due to point charge is given by kq by r square. So I'll write this way, k q2 by r2 square. Okay, the distances are separate, you can see charges are separate, k and k you can cancel. Okay, now q1 we know that it is 16 microcoulomb, so micro will get cancelled. We need not bother about that. R1, the distance of the charge, first charge, 16 by x square. Distance of the second charge, the second charge, which is 4 microcoulombs, and here the distance of the second charge, which is 3 minus x square. Okay, so what can we do? We can actually take this as 16 by 4, which is 4, and on this side we'll have x by 3 minus x, right? So 16 by 4, and on that side we'll have this whole square. So basically x minus 3x will be given as 2, which is plus or minus, but here the plus will give us the correct answer. Okay, you can check that. So basically the other way around you'll get a different answer. The point will be somewhere here or here, which cannot happen in case of two positive charges. Okay, the force will only cancel in somewhere between them in case of two positive charges. Okay, what happens if this is positive and that was negative? That is your exercise. You tell me if this was positive, okay, and this is negative, where will be the force 0? Okay, let me know in the comment section. So here x is equal to 2 3s are 6 minus 2x. Here we'll get 3x is equal to 6, x is equal to 2. Okay, x is equal to 2. So the x is 2, or from here it is 1, right? So you can either say 2 meters from 16 microcoulomb, or if you say 1 meter from 4 microcoulombs. So that is your correct answer. Okay, so that's how you solve it. Over to the next section. Section number 7, which is properties of field lines. Actually there are only 11 sections. At the start of the chapter I think I told you 15, but there are only 11, which means we are nearing the end of this chapter. And yes, it was that quick. So coming to field lines are basically, so this whole concept of electric field is imaginary. So field lines are basically imaginary lines or curves, so that if you draw a tangent to that curve, you will find the electric field at that point, the direction of the electric field at that point. Okay, so that is basically what is meant by field line. Okay, so if you have a field line like PQ, and if you want to find the direction of the electric field at point S, you basically draw a tangent at that point, and that tangent will give you the direction of electric field. Okay, these are a few properties of electric field. So let's briefly go through them. Electric field begins at positive charge and terminate at negative charge. You can see it through diagram also. It begins at positive charge. Here you can see that positive charge, the field is radially outward. Okay, it's in 3D like a sphere. Okay, it's radially outward, and which means it is starting at the positive charge. Here there is no negative charge. So in this case, suppose here we have an isolated positive charge, so it will start at the positive charge and terminate at infinity because there is no negative charge, suppose. Okay, and then it terminates at negative charge. Here you can see the negative charge has a field radially inward. So basically, if there is an isolated negative charge, the field will start at some infinity and terminate at the negative charge. Okay, so electric fields begin at positive charge and terminate on the negative one. Okay, and here we also use the convention that the number of field lines will be proportional to the strength. Okay, so basically the number of field lines that you draw around a charge will show the strength, its magnitude. Okay, so 2q will have 4, suppose 2q has 4 field lines, then q should have half the number of that. Okay, so that number should be kept proportional. Or in NCRT, basically they draw thicker lines, okay, to show strength of the field. Okay, what they will do is, suppose this is q, they'll draw same number of lines for q and 2q, but for 2q they will make it thicker. Okay, this is also a convention which might be used in textbook, but it's not feasible to use while writing. So remember both these conventions. Okay, so they might use thick lines or thin lines, or in this case you can use number of lines as the distinguishing parameter between the strength of the two fields, right? So now let's come to this. Here we have two field lines can never intersect each other. Can you tell me why? Because there will be ambiguity in direction, right? Field lines tell you about the direction of the electric field, right? So if you have two field lines crossing each other, then this field line, the tangent will say it's along this direction, and the tangent to this field will say it's along this direction. Electric field at a point will be in two different directions. So what will be the mental state of the charge? Idhar chala, main udhar chala. Okay. So that is so cringe. Okay, so because the charge will be confused, right? If there is such a case, the charge will want to go in this direction and that direction, because F is equal to QE, right? The force on the charge depends on the electric field, right? So if electric field has two directions, the force will have two different directions, which is very absurd, right? So electric field cannot have two different directions at a given point. Okay, so that's why we don't have two field lines crossing each other. Okay, this is because we cannot cause ambiguity in direction of electric field. Okay, then we have fourth property, which says uniform electric field. So this is how you depict a uniform electric field: straight parallel lines which are uniformly spaced. You'll often see this being used between the plates of the capacitor. Okay, so there we have uniform field. Okay, these are the lines that depict uniform field. Okay, now finally coming to the fifth point, which says electric field lines do not form closed loop. Okay, of course it will be radially outward, radially inward. They cannot form closed loop. Okay, no field line will be like, if you have a charge, it won't form this way. Okay, they don't form closed loops. Okay, and this is not a loop. This is starting at positive, terminating at negative. So it's not a loop. It is starting and terminating. Starting and terminating. Okay, it's not forming a loop. Okay, this is, by the way, dipole, because these are two charges, equal and opposite charges, which are separated by some distance. Okay, we'll discuss dipole in the next section. So these are field lines due to different charges. This is due to positive, this is due to negative, this is due to dipole, plus and minus. Okay, started positive, ended negative, and some distortion due to the presence of this minus q. Otherwise it is, on the other side, it is radially outward, radially inward. Okay, and here if you have two positive charges, they will repel each other, right? The field between them might get cancelled in the one of the cases that we saw before, right? So field between them might somewhere at a point will be zero, right? They will cancel out each other. The field lines will never cross each other, okay, and they will repel each other. You can see the field lines moving away from each other, okay. So that is in a sense the field of your electric field. Let's move to the next section. Let's now discuss about electric dipole and what happens when we place the dipole in an uniform electric field. So basically dipole, as I told you earlier, it is a pair of equal and opposite charges separated by a fixed distance, right? So here we have minus q and q separated by a distance 2a, okay, or you can say it is d. We say 2a because we want to define the center of the dipole, this point O as the center of the dipole, so it's a, okay, 2a. Okay, so dipole moment P, this is a vector, this is called dipole moment. It is defined as P q into 2a, okay, charge into distance of separation, okay. Remember that dipole moment is a vector and its direction is given from the negative charge to the positive charge, okay. So P is the dipole moment. It is given as charge times the distance of separation q times 2a, okay, and direction is from negative to positive. Now there are two derivations which are important over here, wherein we find the electric field at the axial point and the equatorial point due to a dipole, and this is what we'll be doing in the next class, in the derivation class that I told you, because derivations will just stretch out this lecture, and here you are just supposed to remember the relations that is of more importance as of now, okay. So we'll be deriving it in the next class. If you wish to follow it, you may, okay. So here the relations that we obtained are the electric field at the axial point meaning a point on the line joining the two, okay. Here is the point, okay, and this distance is assumed to be r, okay. So this r is very much greater than a. In case of dipole, this a is very small, this fixed distance is very small, okay. So if this distance is very much greater than the distance of separation, then the approximated relation is this, okay, 1 upon 4 pi epsilon naught 2p by r cube, okay. P is the dipole moment, this is k, this is r, okay. Then we have at the equatorial point. Now here you can note that the direction of the electric and the electric field at axial point and the dipole moment is the same. You can see negative to positive, and here also the field will be along that direction only, negative to positive, okay. So field and dipole moment are in the same direction in the axial case, whereas in the equatorial case you will see a minus sign over here, okay. So equatorial basically means somewhere on the perpendicular bisector of this two, okay. So this is the center of the dipole and we have the perpendicular bisector. So at some point on the perpendicular bisector of this two, we'll have the field at equatorial point, okay. That is the equatorial point, and we obtained it as minus 1 upon 4 pi epsilon naught. This is k, this is p by r cube, okay. You can see that it is half at that of the axial point, okay, and it is opposite to the direction. Here the field is equatorial point, okay. It will be more clear when we derive it in the next session, okay. So minus q to plus q, the dipole moment is in this direction, the equatorial field is in the opposite direction. You'll come to know when we derive this, okay. So here the axial field, you can see that the magnitude of the axial field is 2 times that of the electric field, okay. Magnitude wise, this axial field can be expressed as 2 times this equatorial field, right. Equatorial is half of axial, so axial is 2 times equatorial, okay, and magnitude because they are in opposite direction, so only consider the magnitude. So if you are given the field at axial point or equatorial point, one of them, you can find the field at other point, okay, without going through this process, okay. Now let's come to this topic wherein a dipole is placed in a uniform electric field. Now uniform electric field, you know, it is depicted this way, closely spaced line, uniformly spaced lines, straight lines, okay. And we have a dipole, here we have plus q and here we have minus q, okay. So you can see the dipole moment will be from here to here, dipole moment is in this direction, and let us see the force on this these two charges, okay. So what is the force given as? Force is given as QE, right? In terms of electric field, force is QE. So on this charge we'll have minus QE, right, opposite to the direction of the electric field, because it is a negative charge. Negative charge will try to move opposite to the direction of the electric field. Okay, so it is minus QE in this direction, and the force on this charge is plus QE, because it is plus Q, so it will be plus QE. Okay, so you can see that this is minus QE, this is plus QE, these two will cancel. So the net force on on a dipole placed in uniform electric field is 0. Very important that you remember this. The net force on a dipole placed in uniform electric field is 0. Okay. Now let's come to this point. What about the torque? Okay, you can see that these two forces are acting along two different lines. Okay, so it will try to rotate this dipole. You can imagine that here it is minus QE plus QE, right? It is trying to rotate. This force is acting this way, this force is acting this way. If they were along the same directions, they would have cancelled. Forces cancel, but here they are constituting a torque since they are along different directions, but these forces are along different lines. That's why they are leading to rotation of that dipole, right? You can imagine that the dipole is rotating in that field. Okay, so that torque, again we'll derive this relation when we come to the derivation session, okay, in the next class. So torque is given as P cross E sin P cross E, which is P sin theta, right? Cross product, so sin theta. So basically you can see that when this dipole, so if I had to give you the example, when this dipole and electric field are along the same direction, right, that time the torque will be 0 because sin theta is 0. Theta is the angle between P and E, okay, P cross E, right? So the angle between them, P and E. Okay, so if the dipole is along the direction of the field, you can see that in this case the torque will be, the forces will be along the same direction, and they will not constitute torque now. Here it will be QE, here it will be minus QE. This and this will cancel, and there is no tendency to rotate, right? These two forces cancel, and the basically the torque will also become 0. So when theta is 0 or 180, maybe this way, so in that case also the torque will be 0, because sin 0 is 0, sin 180 is 0. You can see that mathematically too, or you can imagine that too. And when it is 90 degree, the torque is maximum, okay, because sin 90 is maximum. Here it is QE plus QE. It will try to rotate with maximum tendency. Okay, torque will be maximum in this case, and the value will be PE. Sin 90 is 1, right? So that's about the dipole. Let us move to the next section. Discuss about different type of charge distribution, continuous charge distributions. We have three of them: linear, surface, and volume. So basically in this we are going to take a charge Q. In linear one, we are going to uniformly distribute it along the length of a wire. In surface, we are going to uniformly distribute it on the entire surface of surface area A. In volume, we are going to uniformly distribute it about the entire volume. Okay, so what is the use? We can find the small value of the charge in the small element. Let's take the case of linear. Okay, here we have distributed the charge uniformly along the length L. Okay, so what if we want to find the charge in the small element dl? Okay, so it's very simple. So the entire length we have charge q. So for dl we'll have charge dq. So how will we find this dq? We just crisscross. Okay, dq will be q by L dl. dq will be q by L dl. Okay, and q by L we have defined it as linear charge density. In all the cases we'll define some. Here we'll have linear charge density as q by L. Here we are spreading across surface, so q by A. Here we are spreading across volume, so q by V. Okay, so that is a very useful format. Okay, so the charge in the small quantity, in the small length, you can directly find it using this lambda. If you know this lambda, you can directly multiply with dl, the amount that you have chosen. That will give you the charge in that particular length. Okay, so similarly for surface, it's distributed over an entire surface. This is surface charge density sigma. Okay, and that dq will be given as sigma times dA. Similar steps over here. So similarly you can do it for volume too, and you will get dq as rho times dV. Here we have defined volume charge density as rho, which is q by V. Okay, so this the charge in the small volume dV will be given as dq is equal to rho times dV. Okay, so this is what we are going to use it in finding electric field due to different continuous charge distributions. We'll use it in the derivation sessions, of course, but today I want you to commit these formulas to the memory. Okay, this lambda, sigma, and rho, and how will you find dq in each case. Okay, so that's about it. Over to the next section. Let's come to electric flux and the Gauss law. Okay, so basically what is electric flux? Electric flux is the measure of number of field lines that are passing through a given surface. Okay, so actually normally, okay, we only take those lines which are passing perpendicular to the surface. Okay, so it's the measure of number of field lines passing through a surface normally perpendicular to the surface. So suppose we have a surface like this, okay, and electric field lines are like this. Okay, so we take only the normal component, so we only take E dot A cos theta. Okay, now this A stands for area. Now you might be puzzled, why is area a vector over here? Okay, yes, we treat area as a vector in this case, and this vector has the direction along the normal to the surface. Okay, so perpendicular to the surface. Okay, so we take only those component of E which are along the direction perpendicular to the area vector. Okay, so E dot A cos theta. Okay, so that is the definition of flux, or EA cos theta. Sorry, E dot, either you can say E dot A or EA cos theta. It's nothing but E dot A, right? So I hope the definition of flux is clear. So you can also write it this way. Okay, you can write the flux as an integration of the flux through the small surface. So you can consider a small surface and calculate the flux, and then integrate it over the entire surface. So you can consider a small area dA, and then consider the flux through it, and then integrate it over the entire dA. This is a process that we are going to use while finding the electric field due to continuous charge distributions. You will see the relations in the next section, but while deriving we'll use this relations. Okay, and coming to Gauss law is very simple. It tells you about what will be the flux in case of, it's very useful in case of symmetry. So it says that net flux through any closed surface is equal to the charge enclosed by epsilon naught. Okay, so if you want to find net flux in any surface, okay, you just have to see what is the charge enclosed in that surface, the charge inside that surface, divided by epsilon naught. And that is such a simple relation as compared to this, right? So if you want to find flux, you can easily do this, and this is the relation. This is basically we are comparing this, and this flux is E dot dA, right? Integration E dot dA, and this is Q by epsilon naught. This is the relation that we are going to use to derive our electric fields due to continuous charges. Okay, so that was about Gauss law. It's very useful in case of symmetry. Okay, otherwise also it's a bit otherwise it's a bit questionable. So, but in case of symmetry, it is very useful. We'll see it in one of the questions, one of the last questions. Okay, so I think that's about this section. Over to the next one. Last section for the day, which is the electric field due to different charge distributions. Here I have given the formula. This is something that we will derive in our next session. So let's briefly go through the formula. So for an infinitely long wire, the formula of electric field is lambda upon 2 pi r epsilon naught. So here the relation of E versus R, the graph is shown, E and the distance R. So here you can see E and R are inversely proportional, so hence this relation. Then we have infinitely long plane sheet. So here in this case we can have a plane sheet or a conducting plate. So in case of plane sheet, it is epsilon sigma by 2 epsilon naught. Okay, in case of conducting plate, it's sigma by epsilon naught. Okay, so that second part is not important, but in case of plane sheet, it is sigma by 2 epsilon naught. Here there is no R factor, so electric field is constant with respect to R. Okay, now let's coming to the third one. Here we have a spherical shell or a solid conducting sphere. So in this case, basically spherical shell and this solid conducting sphere both can be treated equally, since any charge given to a solid conducting sphere will always reside on the surface. Okay, and spherical shell also the charge will be on the surface only. Okay, so they can be considered identical. Okay, since it's conducting, the charge will be only on the surface. Okay, so here there are three different cases. It can be inside the sphere, so electric field inside the sphere, on the surface of the sphere, and outside. Okay, so electric field inside the sphere is 0. Okay, in case of spherical shell or solid conducting, basically because the charge, as I said, is on the surface, right? So no charge enclosed, no flux, no field. Okay, so That is the idea over here. Then on the surface we'll find it to be kq by r square. Here capital R is the radius, small r is the distance. Okay, and E outside the sphere is kq by r square. Okay, so here we can see the relation. So initially inside the sphere, okay, inside the radius, so up till the radius it is 0. Okay, electric field is 0. Then it has some value kq by r square, constant value, right? K is constant, q the charge we have given is constant, and r square the radius of the sphere is constant, so some constant value. And after that it varies inversely as r, okay, as r increases. So that is the fall over there. Okay, finally coming to solid non-conducting, what is happening to be solid non-conducting sphere. In this case there will be charge inside the sphere too. Okay, it will not give the entire charge on the surface only. So when you give the charge, it's non-conducting, so it will hold the charge. It will not just go and reside on the surface only. Okay, so in this case there will be charge inside too. Okay, and due to that there will be difference in this relation. Otherwise this and this, if you see kq by r square, kq by r square on the surface, outside the surface kq by small r square, kq by small r square, this is same. Okay, only this thing will change, which is kqr by r cube, kq small r by r cube. This is capital R, this is radius, small r is for distance. Okay, so inside you can see that it is a linear variation. E is directly proportional to r, linear variation, and then some constant value, and then it falls as r square. Okay, 1 by r square. Now finally let's come to this one. This is a question based on Gauss law. So we have a charge q which is placed at the center of a cube. What is the flux linked with all the faces and with one face? Okay, for a flux linked with all the faces, it's very simple, as we have charge q. So what is flux according to your Gauss law? So all the 6 faces will be basically q by epsilon naught, right? Flux linked with all the 6 surfaces, okay, or the entire cube will be q by epsilon naught, charge enclosed upon epsilon naught, right? What about only one face? Okay, now this is a very symmetric condition, and since it is symmetric, we can say that in this case, in the case B, the flux will be q by 6 epsilon naught. There are 6 faces, and the charge is at the center, which is the major point over here, so that the flux linked with every face will be divided equally. So 6 faces, so flux linked with one face will be 1/6 of the total flux. Okay, so if this charge was not at the center, so since it is at the center, the flux linked with all the faces is same. But if it was not at the center, then the story would have been very different. So as I told you, Gauss law is very helpful in case of symmetry, otherwise it is not. Okay, so if it was not at center, suppose it was close to this face, the right hand side face, here the flux would be more and here the flux would be less. Okay, so that's the thing. So since here it is at the center, here we can say the option for B, the answer will be 1/6 of the total flux. Okay, since symmetry follows, it follows by symmetry. Okay, and this is something which you may want to note and come around the next time, and we'll derive the equations for this. Okay, we'll see how come we obtain this relation. So that's all for today's lecture. I hope you really enjoyed it. Do let me know if there are any doubts in the comment section. Do let me know if I missed out on some topics in the comment section, and do answer the questions which I raised in between along this lecture. Okay, and do join me in the next lecture if you wish to know about the derivations, or do join me in the lecture after that, where we'll be discussing the next chapter from 12th standard. Till then, keep enjoying physics.